So far, we've talked a lot about how to measure and quantify the rates of reactions, but we haven't talked a lot about things that affect those rates. One of the big things that affects reaction rates are temperatures. Most reactions speed up when you get to a higher temperature. And the reason is that for reactions, if we look at their reaction energy diagram, where we have usually time on the x-axis and energy on the y, it always looks something like this. So this would be an exothermic reaction where I ultimately end up at a lower energy. But even for these exothermic reactions, we have this little hump here, which is called the activation energy or activation barrier, this hump right here. This is the amount of energy it takes to get my reaction started, and this is required for every single reaction. Even exothermic reactions, even if they give off a bunch of heat, they have to get over this hump first. Well, if I make my temperature higher, I give my molecules more and more energy, and they're more likely to have enough energy to get over this hump. So think about taking a bunch of little kids, right? You give them a bunch of energy, give them a bunch of sugar or something like that. They're more likely to be able to run around, run over a hill, things like that. So we're essentially giving them more energy when we get to this higher temperature. So we can actually quantify this relationship using the Arrhenius equation right here. Now K, that's just the rate constant we've been seeing in all of my other rate laws. And if we recall, a big K means that I'm going to have a faster reaction. Small k means a smaller reaction. And it's dependent on a few important things. A here is my frequency factor, which is how often my reactants even try to go over that activation barrier. If they don't try, my rate's going to be really low. But if they try really frequently, then I'm going to have a higher rate there. Then E, this is just the natural E, like that exponent button in your calculator, and it's E raised to the power of negative EA over RT. And EA, this is that activation energy. This is the height of this barrier right here. So the higher that barrier is, we can see mathematically the smaller my rate constant is going to be and the slower my rate, which makes sense. If you have a really high barrier, it's going to be very unlikely that your molecules have enough energy to actually react, and therefore most of the time it's not going to happen. And so your rate's going to be very, very small. Most of the time your reactants don't turn into products. But if you have a very small barrier, then my molecules are more likely to have enough energy to get over it. Think about climbing a big hill versus a small hill. The rate at which you can climb a big hill tends to be a lot slower than the rate at which you can climb a small hill. And so our activation barrier has the exact same effect. R, that's just a constant we've seen before, 8.314 joules per mole Kelvin. So we just got to remember that constant. And T is my temperature, which is always in Kelvin. So as my temperature increases, it's going to cause this number to be overall bigger, and therefore my K is going to be bigger. So as your temperature increases, your rate constant will also increase. Again, because we're essentially giving my molecules more energy, and they're more likely to be able to cross that activation barrier. So we can do a few different things with the Arrhenius equation. We could look at my rate constant, calculate it at a bunch of different temperatures, and see how much faster my rate would be at those temperatures. The other thing we can do, because chemists love to do this, is try and imagine this like a straight line. So this is called an Arrhenius plot, and all we've done is if we take this equation and rearrange it. So first we take the natural log of both sides, and then we rearrange it a little bit, we get this equation right here, which a chemist looks at and says, ooh, this looks like a y equals mx plus b equation, where my x is equal to 1 over the temperature, and my y is equal to natural log of k. So what this means practically is that if I'm in the lab and I measure the rate constant for a reaction at a bunch of different temperatures, I can make a graph where on the x-axis I put 1 divided by the temperature, and on the y-axis I take the natural log of all my rate constants and plot them against the 1 over t. I should get this straight line. The slope of that straight line, if we look here, should be equal to negative EA over R, because this equation corresponds to a y equals mx plus b. Meanwhile, the y-intercept b should be equal to the natural log of A. So if I did this reaction a bunch of different times at a bunch of different temperatures, I can actually get out this activation energy right here and the frequency factor for my reaction. So let's look at a couple different ways that we could be asked questions about the Arrhenius equation and how we choose which equation is going to be better. So here's one example. The rate constant of a reaction at 32 degrees was measured to be 0.055 per second. So that's our rate constant, that's K. Let's keep that in mind. If the frequency factor, so frequency factor is A, is measured to be this, what is the activation barrier? That's another word for activation energy, so that's what we abbreviate EA. And of course, 32 degrees Celsius, that's my temperature. So we can see that we're given a temperature, a rate constant, a frequency factor, and we need to solve for the activation barrier. Now, these equations are totally equivalent, so I'm just going to use the one that's more convenient. In this case, because I want to solve for EA and it's part of an exponent over here, I think it's going to be more convenient to use this one. I could have used the other one, but this one I think is going to be more convenient. So all I need to do is plug my information in here. So I'm going to take the natural log of 0.055, and that's equal to negative EA. R, of course, is just a constant, so that's just 8.314 joules per mole Kelvin. I need to do 1 over my temperature. Now don't forget, temperature is always in Kelvin, so I need to take my 32 and add 273 to it, which will give me 305. So I'm going to plug that in Kelvin. See, my Kelvins here are going to cancel. And then plus the natural log of my frequency factor, which is 1.2 times 10 to the 13th per second. So now I just need to do a little bit of algebra. So I'll calculate this and then subtract it over to the other side. So I'll subtract it from that. And then I can multiply both sides by 8.314 and 305. So overall, when I do the algebra, I find that my activation energy is going to be 8.37 times 10 to the 4th. And I see that my kelvins have canceled, and I'll eventually move this up to the top. So that'll be joules per mole. So this is one way a question could be asked. It gives me a lot of my numbers and asks me to solve for another one. Sometimes it'll ask you to solve for K, sometimes for A, and you just have to plug in the rest of the numbers and then do some algebra. Another thing it can do is try and give you a question graphically. So here it's giving you a plot. It says, based on this plot, determine the activation energy and frequency factor. And the key thing here, because it won't always say Arrhenius equation up top, we'll just have to know that, is that we see 1 over temperature, natural log of K, and it's asking about activation energy and frequency factor. That's what tells us these are Arrhenius problems, because these are the only problems where we talk about activation energy or frequency factor. Anytime it's giving you a graph, we use this equation. But what we have to do is compare it to the equation they've given us. So they made a graph and they have y equals negative 21.12 times 10 to the 4th x plus 26.8. So what we have to do is see what these have in common. So we know that on the x-axis is 1 over t, so these correlate. On the y-axis is natural log of K, so these correlate. So we have to recognize, okay, if those are the two equations we're setting equal, they're really representing the same thing, what we can do is set these parts equal. So the slope here, the negative 21.12 times 10 to the 4th, must be equal to negative EA over R, because we see that's what the slope is in this top equation. So all we have to do to solve for my activation energy is, first of all, the negatives cancel, so we can make those both positive, but we multiply by R, where R is 8.314 joules per mole Kelvin. So that'll cancel on this side. On the other side, we'll just do the math, and we find that we get 1.76 times 10 to the 6 joules per mole. And that's equal to my activation barrier, EA. So the key thing here is recognizing that this equation is equal to this equation. So now we do the same thing. That was my first answer. That's my activation energy. I also need the frequency factor. So I need to recognize, okay, my y-intercept is equal to natural log of A. 26.8 is equal to the natural log of A. Well, we get rid of that natural log with E. So really simple, A is equal to E to the 26.8, which ends up being 4.36 times 10 to the 11th.